Hi Lena, welcome on board to this Q&A session for the topic Atmosphere, its properties and standard atmosphere entitled to the subject Flight Mechanics. In this session, we will be focusing on the question analysis, the book reference, important concepts, formulae and solutions for this particular topic. Let me switch on over to the blog which consists of these resources. So here we are on the Age of Aerospace blog and the GATE Aerospace Engineering page. Now let me scroll down to the flight mechanics subject. So all the materials are provided over here. Now here we are on the flight mechanics tab. Here we can see the resource, the notes provided as a document. And now starting with the question analysis, here we can see the question analysis for the core topic basics, which is under the subject flight mechanics. So under this core topic basics, there are about 11 topics, subtopics. Now, in this session, we will be focusing on this particular topic, atmosphere properties, standard atmosphere. And we can see on the basis of question analysis, they have been asked, there have been one mark in 2015, and there are two marks which were asked in 2008 and 2018. Now, this seems to be an important topic. Getting to the book reference for knowing about in detail about this topic, atmosphere properties and standard atmosphere, I recommend you to go through the Introduction to Flight by J.D. Anderson, and for further reference you can refer to the Aircraft Performance and Design by J.D. Anderson. Here are a few important concepts which you need to know under this topic. So basically, starting with altitudes, you need to know the five different types of altitude: the geometric, absolute, geopotential, pressure, and density altitudes. And now getting over to the atmosphere, we need to know the ranges and the names of the five basic atmosphere. So, starting with troposphere, which ranges from 0 to 11 kilometers, the stratosphere, which ranges from 11 to 50 kilometers, the mesosphere, which ranges from 50 to 80 kilometers, and further proceeding to thermosphere, 80 to 700 kilometers, and then moving on to the exosphere, about 700 to beyond. And one other important thing is the ISA chart. We need to know the basic variation of temperature. So here we can see the basic variation of temperature with altitude. So this is provided by using the ISA or International Standard Atmosphere chart. And in this ISA chart, one particular point of interest is the lapse rate. So here we can see there are about four different lapse rates provided in the figure: A1, A2, A3, and A4. So A is nothing but the symbol of the lapse rate, and if we know these lapse rate for this particular regions, it will be beneficial. So here we can see the lapse rate for A1, that is 0 to 11 kilometers range. This gradient layer, the lapse rate is minus 6.5 into 10 to the power 3 Kelvin per meter. This is pretty much important, and this is the most commonly used lapse rate among these four. But if you know all these four, it would be beneficial for you. Now, moving on to the formulae portion. Uh, Before getting into the formulae, we need to know the standard sea level conditions which we'll be using throughout the problem solving session, or even throughout the syllabus, and even into the propulsion portion of the GATE Aerospace Engineering. So here, the pressure at sea level condition, that is datum or zero altitude, is 101.325 kilopascal or 1.01325 pascal into 10 to the power 5 pascal, or you can also write it as 1.01325 bar. So it depends on you. And moving on to the density, it is 1.225 kilogram per meter cube, and temperature is around 15 degrees Celsius, which is in Kelvin 288.15 Kelvin, which is nothing but 273 Kelvin plus the Celsius, that is 15 degrees Celsius. So here, this is how you convert the temperature from Celsius to Kelvin. And further, the gas constant of air 287 joules per kg Kelvin, and further acceleration due to gravity for Earth. So these are the basic standard sea level conditions which we'll be using further. And now getting to the core formulae portion, uh, we can see here the formula for altitude. So this is a formula for absolute altitude, which is a summation of radius of Earth and geometric altitude or height. And further, the variation in gravity g is nothing but g naught times the radius of Earth divided by the geometric height and square of it. So g naught is nothing but 9.81 meter per second square. Basically, the acceleration due to gravity is varying even for Earth with altitude, but the variation is minor. So we basically take a standard constant value 9.81 meter per second square. This is from basic physics. And now about the geopotential altitude, which is symbolified as h. This is nothing but the ratio of the radius of Earth times the geometric height by radius of Earth summation with the or summed with the geometric height. So this provides us with the geopotential altitude or geopotential height. Now we consider the radius of Earth r as 6371 kilometers, and further from the basics of physics, we need to know the hydrostatic equation, and we need to know the terms and symbols for it. So the basic hydrostatic equation dp is equal to minus rho g h or minus rho g naught dh. And further, it is beneficial to know the equation of state p is equal to rho rt, which we will be using further. Now these two equations which are provided over here, the isothermal layer and the gradient layer. So these both are very important equations considering the atmosphere, its properties, and standard atmosphere. So there are two different equations: the pressure ratio and density ratio for isothermal layer, where the temperature varies, doesn't vary, or the T is constant, and the next layer is the gradient layer, where the temperature isn't constant. So that is the basic difference between isothermal and gradient layer. So these both formulas are required. The pressure and density ratios for isothermal layer and the pressure and density ratios for gradient layer. Now, when we move forward, there is a next topic, classification of aircraft. From the question analysis, we did see that there have been no questions asked from this particular topic, classification of aircraft. Still, it will be beneficial to know to get a clear cut perspective of this. Now, let's get solving the questions. So, here, now getting into the first question. So, this is a 1 mark question asked in GATE 2015. So let's read out the question. Now, before getting into the question, here is the strategy which I'm going to follow, and I also suggest you to follow this. So, allot some particular time to read the question clearly and point out the basic requirements and the givens of the questions. And further, while learning, do know the reason for selecting the option, and also do know the reason why you haven't selected the other options, so or the reason why the other options are wrong and this particular or the answer is correct. So here now getting to read the question, they have asked consider the density and altitude at the base of an isothermal layer in the standard atmosphere to be rho1 and h1 respectively. So the thing they have provided over here is the density and altitude. They have been talking about density and altitude in isothermal layer. So isothermal layer, from the name itself, it means the temperature is constant in this layer, isothermal. So next, then in the next part of the question, they have asked the density variation with altitude rho in that layer is governed by. So they are basically asking an equation, and what they are asking is the density variation. So we need the density variation for isothermal layer. So the formula for it will satisfy the answer for this question. So this is a pretty direct question, and here are four different options provided. And we know from the formula for isothermal layer, the density ratio, the density variation is nothing but the density ratio is E power minus G naught by RT times H minus H1. So this is a direct question. We need to see the formula and see the resemblance for it. Now clearing out all other things. So we need this particular formula in the any one of the options. So here we can see the option A has the same formula written over here. Rho by rho 1 is equal to E power minus G naught by RT times H minus H1. Now the correct answer must be A. Regarding other options, there may be small points which have been altered. So as far as option B is concerned, the H minus H1 term is totally reversed. So H1 minus H. H1 is nothing but the base layer. So for isothermal layer, it is about 11 kilometers. So that's the change. And as far as option C is concerned, they have inversed the ratio RT by G naught, which is not the formula. And here, in similar case, they have reversed both the ratio of G naught by RT and H minus H1, and they have messed up with this. So, analyzing all these four options, option A must be correct. Let's see the answer. Yes, option A is the correct answer. Now, moving on to the next question. So, here we have a 2 mark question from GATE 2008. And the question is, which of the following statements is true as the altitude increases in stratosphere of international standard atmosphere? So they have basically asked the statements which are true. So they have mentioned the stratosphere and the variation of properties or parameters with increase in altitude in international standard atmosphere. So this and a question can be answered by knowing the ISA chart. So here we see the international standard atmosphere chart, and they have plotted the typical variations of different properties, the pressure, density, and temperature along the increase in altitude. So this is on y-axis is the increase in altitude, and in x-axis is the parameters. Now the parameters which they have discussed is temperature, pretty much the same in all the options, and dynamic viscosity, pressure, speed of sound, and density. So they have basically talked about five different properties of atmosphere, and one particular point of interest is the layer which they are talking about, the stratosphere. So here, a stratosphere, which basically means the layer ranges between 11 to 50 kilometers. So here we can see it will be ranging between 11 to 50 kilometers. So this particular range is the stratosphere of international standard atmosphere. This is the layer of atmosphere. And in this layer, we can see the temperature is either constant or increasing. So this is a scale for temperature. And here we can see it is either constant, the straight line, or increasing. So it is in decreasing. So any option which mentions the temperature decreases with increase in altitude in stratosphere is wrong. So of all these four options, option C says that temperature decreases with increase in altitude. So this option must be wrong. Similarly, when we get to know about the other options, we can see that as we said mentioned, the temperature either increases or remains constant with increase in altitude in stratosphere. Okay, now, these three options are similar, and now we have to consider the other parameters. Now, dynamic viscosity. Talking about dynamic viscosity, the dynamic viscosity of gases and speed of sound increases with temperature. So, dynamic viscosity is nothing but mu, and speed of sound is nothing but A. So, we know that the basic formula for A is square root of gamma RT. So, here we can see that speed of sound is directly proportional to the temperature. So if temperature increases, the speed of sound also must increase. Here we can see the temperature is either constant or increasing. So any option mentioning that speed of sound decreases is wrong. So speed of sound decreases is wrong. Similarly, we had to know that the dynamic viscosity also increases with temperature. So the dynamic viscosity for gases increases with temperature. So here it is mentioned as the dynamic viscosity decreases. So this option is also wrong. And one particular point of interest is that the dynamic viscosity of liquids on an contrast decreases with temperature. So for gases it increases with temperature, and for liquids it decreases with temperature. So we have crossed out two options, and the remaining options we can see that the temperature remains constant and pressure increases. So talking about the pressure, uh, here we see the pressure plot, and this is a scale for pressure. With increase in altitude, we can see the pressure keeps on decreasing. So pressure must decrease with increase in altitude. But here it is in opposite, so this option is also wrong. Now we are left out with the option D. So knowing about the correctness of this option, the temperature remains constant because it's remaining constant or increasing. Okay, remains constant. And density. So talking about density, the density is plotted over here. This is also decreasing with increasing in altitude. So here the density decreases. Thus, this option D must be the correct answer. So seeing the answer key, the option D is the correct answer. That is, the temperature remains constant and density decreases with increase in altitude in the stratosphere. Moving on to the next question. So here is a 2-mark question from GATE 2018. So reading out this question, so this is a numerical answer type question. This doesn't have any negative markings. And one other point to be noted is that from this year there are different patterns of questions. That is, they will be asking questions such as multiple choice questions. So here in this case only one option was correct, but in that new pattern of question there may be multiple options. Either D and B may also be the correct answer. Getting to the question, reading the question, we know that assuming ISA standard sea level conditions, they have provided the sea level conditions, temperature in Kelvin, density in kilogram per meter cube, the acceleration due to gravity, gas constant. So they have basically asked the density of air at Leh. So Leh is a location near Ladakh. So here they have specified that Leh is at an altitude of 3,500 meters and above mean sea level. So they have basically asked the density at this particular location, which is at an altitude of 3,500 meters. So talking about the density and this particular altitude, we can see that this 3,500 meter range is within the troposphere, that is within 0 to 11 kilometers. So this must be lying in the gradient layer of atmosphere. So this is 11 kilometers and 0 kilometers. 3,500 must be somewhere over here. So to know the density at this particular altitude, we can solve in by substituting the formula for gradient layer. So for gradient layer, we know that T is equal to T1 plus A H minus H1. So T1 and H1 is nothing but the sea level conditions, and H is the height at which we are interested to find the parameter on, and T is the temperature at that particular height. In this case, it is 3,500 meters. And we know the formulas for pressure ratio and density ratio. And for this, we need the density ratio as they are asking in the density. So writing down the given portion of the question, you can see the sea level conditions were given, and taking the sea level conditions with the subscript 1, T1 is 288.16 Kelvin, H1 is 0 meters, that is sea level. Sea level is nothing but the altitude H is equal to 0, and H1, as we are taking the subscript for sea level conditions as 1, and the height at which we are interested to find the density on is 3500 meters, and as it lies in the gradient region and within the troposphere, the first gradient region, the A1, is minus 0.0065 Kelvin per meter, or 6.5 into 10 to the power minus 3 Kelvin per meter. And the density at sea level condition is 1.225 kilogram per meter cube. And G naught value is also constant, 9.81 meter per second square. And solving in for solution, so first applying the 4.1 formula, we can see that T is equal to T1 minus plus A times H minus H1. So here T1 is the sea level temperature. It is 288.16 minus the lapse rate A 0. Minus 0.0065 times H is the altitude at which we are focusing upon, that is 3500 meter, minus H1 is the sea level height, which is 0 meters. So when we try to solve this, we obtain a temperature as 265.41 Kelvin at an altitude of 3500 meter. Now, as we have found out the temperature at that particular altitude, we are substituting the value in the density ratio formula for gradient layer. So density ratio at 3500 meter altitude by density at sea level is equal to the formula T by T1 power minus G naught by AR plus 1. So here we have found out the T as 265.14, and just kind of resume it. So now we know the density at the sea level altitude, 1.225. So here, when we substitute all the values in this particular equation, we obtain the density at 3500 meters altitude. So here we can see it is rounding off this value. This whole section is rounding off to a value of 0.7045, and when we multiply it with 1.225, we obtain a value of 0.86 kilogram per meter cube. So this must be the answer, or density at 3500 meter altitude. Let's check the answer. So as per the gate answer key, it must lie between 0.85 to 0.88. So 0.86 is a value pretty much satisfies the range of answer. This is how we solve a numerical answer type question. That's it for this session. Thank you.